Greetings and welcome. In last session, we have seen about the aircraft refrigeration system, its purpose, its types, selection of different types of aircraft refrigeration system based on the dry air rated temperature. In this video session, specifically, we are going to study the system that is simple air cooling system. This system is preferred for the low speed aircrafts which are moving or flying at a low altitude level from the ground. We will see or we will study this system in two parts: construction and working, and analysis. So part A we say construction and working, and part B is analysis, where we will find the different formulas to find the parameters, performance parameters. So let us see, this is the construction diagram of the simple air cooling system. Mainly it consists of different parts which are mentioned over here. Here we can see this is the entry of air, ambient air to the aeroplane. So when it is entering, it is coming across the part that is diffuser. In the diffuser, pressure of the air is slightly increased. That is why it is called as ramming of the air. This ramming action is taking place in the diffuser section. Here simultaneously we can see this is the pressure line of ambient air or entering air. Point number 1, pressure P1. 1 to 2, this is a process, that is ramming process, which is taking place in a diffuser section. Now here we can see, here are the two ways of taking that process. This is a vertical line, that is a dotted line. It shows the process that is taking place ideally, isentropic ramming process. So in this case, entropy is remaining constant, and this is the actual path followed by the process from 1 to 2 in ramming. Onwards, 2 to 3 process is taking place in the next part, that is a compressor. Here in a compressor, pressure of the air and temperature of the air is simultaneously increasing from point number 2 to 3. Here also the process is taking place in two ways. Dotted line, that is a red line, is showing ideal process, isentropic compression, and 2 to 3, this continuous line is showing that is actual process. So here from 3, when the air is coming out from the compressor, its temperature and pressure is increased. This we have to reduce temperature. So that is why it is necessary to remove heat content from that air. So that is why this air is passed through this air cooler. It is one kind of heat exchanger, and as it is used for cooling of air, that is why it is called as air cooler also. So that is third component. This air cooler reduces the temperature of air from 3 point to 4 point. This process is obvious constant pressure process. This is what heat rejection is taking place at a constant pressure. So pressure P3 and P4 are same. From the air cooler, that air which is getting cooled, that air cooled by the air. Now this air is used from the main air, ambient air, because this air is a cold air normally. So this air is bypassed, and this air is passed through this heat exchanger. So when this hot stream from the compressor and cold stream from the bypassed air is coming across, then here the air which is coming out, that is getting cooled. So 3 to 4, in this way temperature of air is reduced. From the 4, this air is passed through the next part or device, that is what? Turbine. It is also called as expander. So what is function of turbine? To reduce the temperature by the expansion process. So here 4 to 5 dash. Here is a 5 dash. This process 4 to 5 dash. Here also this process is shown by the 2 path. This is a vertical dotted line which is moving from 4 to 5 dash downward direction, that is isentropic expansion of the air. And 4 to 5 continuous line, it is the actual expansion of the air. So when this air is coming out of the turbine, its temperature is near about below the ambient temperature. So this air is passing to then the cabin. So when this air is passing to the cabin at point 6, that is a cabin temperature is achieved, and that is mostly prepared in the range of 22 degrees Celsius to 25 degrees Celsius. So in this way we have now seen or studied the construction and working of simple air cooling system. Now we will see about its analysis, means performance parameters, efficiency, pressure temperature ratios, and COP, that is coefficient of performance, is the next part. So in the analysis, we will first of all see, we will start from the process, that is a ramming process. In the ramming process we see, here we see the point 2 dash and 2, that is at the same temperature. That is why in this case the temperature T2 and T2 dash is a identical temperature. Okay, so to find the T2 dash we have to use equation that is used for the analysis purpose. Here is the equation, that is T2 dash upon T1, that is equal to 1 plus gamma minus 1 upon 2 bracket into Mach number, square of the Mach number. So in this way here we can write this formula T2 dash. Obviously this is also applicable for the T2, because already we have seen that is temperature 2, a temperature of point 2 and 2 dash is identical. So this formula becomes in this way, T2 or T2 dash is equal to T1 bracket 1 plus gamma minus 1 upon 2 into Mach number square, where the gamma is adiabatic index. Normally value of it is taken 1.4 for the calculation purpose. It is also a ratio of Cp to Cv of the air that we have studied or we know in the subject, that is air standard cycles in engineering thermodynamics. This formula we use, Cp upon Cv, that is constant heat, specific at a constant pressure, and specific heat of a specific volume, Cv, that is constant volume, Cv. Okay. Now here Mach number can be calculated or it may be given in the numerical. If it is not given, then we have to use the formula, that is Mach number is a ratio of plane velocity, means aircraft velocity, to the sonic velocity. Sonic velocity is also called as acoustic velocity. Ratio of these two, that is called as Mach number. Sonic velocity is normally taken equal to 340 meter per second. If it is not given, then again we can use to calculate this velocity, sonic velocity. There is a one formula. That formula is under the square root gamma r T1, gamma adiabatic index 1.4, R, that is a specific gas constant for the air, that we take 0.287 unit kilojoule per kg Kelvin, and T1 is a absolute temperature of the air which is entering. Absolute means in a Kelvin, we have to convert degree Celsius to Kelvin by adding it, that value, to 273. So absolute temperature. So by using this formula we can calculate the sonic velocity. Then aircraft velocity is given in the numerical, we can find the Mach number, and further by putting the value of Mach number we can calculate the value of T2 dash. T2 dash can be calculated by another way also. If in the numerical, if ramming efficiency of that process is given, so by using that concept also we can find the T2 dash. So for that purpose, here we will first of all see how to find. So here we know that these are the three lines. This is the ambient pressure of air entering. This is a point number. This is a line, ramming line. So in this diagram we can see here, this is a ambient air line. This is the ramming process by the two ways. This is the ideal process, isentropic ramming, and this is actual ramming. So this is a 2 dash and this is a point number 2. So first of all we have to find pressure P2 dash, and then P2 dash value that we can put in the pressure temperature ratio formula. So for that, in the numerical we are given the value of, that is, RAM. So ramming efficiency. So ramming efficiency is given. What is ramming efficiency? It is a ratio of actual pressure rise to ideal pressure rise. Here we see actual pressure rise means this P2 minus P1 divided by P2 dash minus P1. That is ideal pressure of the air at the exit of ramming or diffuser. This process is taking place in diffuser section. We call it as ramming process, ramming action, ramming of air. So by using this formula, efficiency formula, we obtain P2 dash. And this P2 dash we put in the formula, that is we know that for the ideal process we can use the temperature ratio and pressure ratio relation. That is what? T2 dash divided by T1 means temperature ratio during the ramming process is equal to pressure ratio. That is P2 dash upon P1 raised to gamma minus 1 upon gamma. So by using this formula we can obtain value of T2 dash. So there are two ways that we have seen in the last. T2 dash is obtained by using this concept where we should know the Mach number. If Mach number is not given, then other one, that is ramming efficiency, should be given. By using by using the value of ramming efficiency, we can, using these two formulas, we can find the T2 dash. Now in the numerical way, the process is taking place ideally only in that way, the numerical given, then we can use the process in that case means here in this way, that is a ramming. 1 to 2. This is the case, then in that case we can use the formula temperature ratio and pressure ratio. This relation we can use. By using this relation we can obtain T2 temperature. Now further part is of the compressor. Regarding the compressor, we can get two formulas for the compressor: temperature ratio formula and compressor efficiency. So these both formulas we can write with the help of this diagram. Here we see we can take help of these two processes: ideal process from 2 to 3 dash and actual process from 2 to 3. So for this we write the formula. That is T3 dash divided by T2 is equal to P3 by P2 raised to gamma minus 1 upon gamma. This is the one formula, that is a temperature ratio. From this we get value of T3 dash, and compressor efficiency. Here is about ratio of ideal temperature rise between 0.2 and 3 dash. This is ideal temperature rise in the main compression process. And this is the actual temperature rise. So ideal to actual temperature rise is given by using this formula, that is compressor efficiency. So by using this formula, by putting the value of T3 dash over here, we can find the value here T3, means exit of the compressor. This we can get value. Next part is where the air is passing from the cooler to the cooling turbine. So here two formulas also used in the analysis purpose. Here we see this process is from the cooler. This is exit of the cooler exit temperature. This is the expansion, ideal expansion. This is actual expansion. This process is taking place in the expansion turbine. So here two formulas that we use, that is first one is a temperature ratio between the points 5 and 4. This ratio is equal to pressure ratio raised to gamma minus 1 divided by gamma. So by using this we can obtain the value of T5 dash, that is ideal temperature of the exit of the turbine. And to find the temperature T5 we have to use efficiency. In the numerical, turbine efficiency is mentioned. So here we can see the ratio of actual temperature drop to ideal temperature drop. Now this formula is opposite to the formula of compressor. Opposite means concept. Here we can see, to memorize, if it's getting difficult, then we can see here obviously efficiency is less than 1. Means if you take this smaller difference divided by larger difference, that will give the efficiency less than 1, because always efficiency is greater than less than 1. So that is why here we have to take actual temperature drop during the expansion process divided by this is the ideal temperature drop. So this is what this we can write here, that is T4 minus T5 divided by T4 minus T5 dash. So by using this formula, you can obtain the temperature of turbine, actual exit of the turbine, actual temperature you can obtain. Now the further part is to find the cooling effect or capacity. So cooling capacity of the system that is in the examination or in the paper, if it is given in a TR, that is ton of refrigeration, then that value we have to convert into kilowatt. So there is a conversion factor, that is 1 TR is equal to 3.51 kilowatt. So this relation we can use in the finding the value of cooling capacity in a kilowatt. Cooling capacity is given Q dot L, that is a cooling load. Now this process we have seen in the diagram. If you see in the main diagram, we will see here, this is the process. This is the exit of the turbine. This air is passing to the cabin. During this journey, whatever heat load is carried by the air, that is called as cooling load. So 5 to 6 process, that for that process we have to write the formula. So thus we can write the formula Q dot L is equal to mCp delta is the basic concept that we use. mCp delta in a thermodynamics, product of mass of substance into specific heat of that substance multiplied by temperature rise during the process of that substance. So mCp delta T. So here, as the substance is or medium of heat carrying, that is the air, that is why here we use here m dot A, means mass flow rate of the air, mass of air passing or circulating through the system. This is a flow rate. Its unit is kilogram per second. Cpa is a specific heat of air, so that is taken 1.005 kilojoule per kg Kelvin. This is a specific heat of air, heat carrying capacity of air. And temperature difference here we can take, that is a T5 minus T6. So here, sorry, T6 minus T5, because T6 is a higher temperature. So product of kg per second into kilojoule per kg Kelvin, and into this temperature difference is in Kelvin. So here we can get cancellation of all the terms. We find here finally this kilojoule per second, and that is what? Kilowatt. So cooling load or cooling capacity of the system is expressed in a kilowatt. To find that, we can use this formula. Now COP. Now COP is what? Coefficient of performance. So to find the COP, coefficient of performance, it is a ratio of, general formula is what? Output divided by input. Output that we have seen now discuss, that is a cooling load capacity of the system. Input is a network consumption, work consumption. So mainly in the diagram we have seen there are two sources of the work where the work consumption is taking place. One is for ramming work and compressor work. So summation of these two work that is nothing but net work. So W dot R, W dot work, as it is in kilowatt, that is why we use here W dot later. R stands for RAM. So this is a MCP, means MCP of air, mass flow rate of air into specific heat of air, multiplied by ramming process is taking place between the points 2 and 1. So T2 minus T1. So this we can calculate. We get this value in kilowatt ram work. And compressor work, W dot C. This is a product of M dot A, CPA. Process in a compressor. Compression process is taking place between the point 3 and 2. So that is why the formula here, temperature difference comes T3 minus T2. So this becomes compressor work. Summation of these two work, that is called as net work. Now here in the diagram, if we see, we have seen expander also. But expander work or turbine work we don't consider here, because that turbine, if you see in the diagram, we can see here. Here if you see, to take out the air, this air which is bypass air, that is passed through this heat exchanger, this air we have to remove. We have to release to the atmosphere. So for that purpose, this fan is rotated. This fan is run because this fan is mounted on the shaft, and that shaft is connected to the turbine. So here, to drive this fan, the power of the turbine is used. So that is why this turbine work is not taken into consideration, because this turbine work is already used for the fan, to driving the fan. So fan work is nothing but turbine work. Now in this analysis also one point is also important, that is a journey of the air through the heat exchanger. So when this air is passing from the point number 3 and it is passing through this heat exchanger, then it is coming to point number 4. So there is a cooling of air from point number 3 to 4 that is taking place in the air cooler. So here in the numerical, sometimes you may be given effectiveness, that is performance parameter of the heat exchanger. So for the effectiveness of the heat exchanger, this formula we should know. So by using this formula, we can find the required temperature. Okay, so this is what T3 minus T4 means. To hot point in the heat exchanger, temperature of the air is reduced from point number 3 to 4. So this is a output of the heat exchanger, and this temperature is increased because of what? Because of addition of heat by the compression process. So compression process starts from point number 2. So that is why here the temperature difference between point number 3 and 2, that is taken here at the denominator, T3 minus T2. So ratio of T3 minus T4, this is a cooling of the air, divided by this is a temperature rise that is due to compression, T3 minus T2. So this formula is used, that is as a effectiveness of heat exchanger in the analysis purpose. So finally, again, already we discussed, that is RAM work, total work. Then by putting the value of this cooling load and net work, we obtain the COP, that is coefficient of performance of the system. So this was a whole video session on the construction and working of the cooling system, simple air cooling system, along with that TS diagram we use for the analysis purpose.